Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through trigonometric identities with the Moivre theorem. This is an application of the Moivre theorem where we can simply express different powers of trigonometric functions. If this is the first time you are visiting this channel or you have been with us, kindly subscribe to support and please do well to share. So let's see what this video has for us. So the Moivre theorem in our previous lessons is just trying to simplify powers of a complex number. You have a complex number z, which is equal to cos theta plus I sine theta. And you want to find the power of this complex number z to the power n. Then the theorem is saying that you don't have to simply try to find the power. Try to take the nth power of this, but rather the answer is simply equal to cosine n theta plus I sine n theta. If it happens you have an r, which is a modulus, then our z, r here, then becomes r to the power n multiplying cosine n theta plus I sine n theta. So all that you are trying to say is if you have a complex number z is equal to x plus iy, then it means that if you want to find z to the power 6, then what do you have to do? The first thing you're supposed to do is to convert from linear to the polar, because the Moivre theorem works with the polar form. So after conversion into the polar, you simply take to the power 6 and apply your de Moivre's theorem nicely. Now let's look at the applications we are going to do for the trick, right? So before we start application, let's look at these identities in complex number. The first one is z to the power n plus 1 over z to the power n is equal to 2 cosine n theta. The second one is c to the power n minus 1 over z to the power n is equal to 2I sine theta. These are very important identities in complex numbers. So that if I have a complex number and I add it to its inverse, then I'm supposed to get 2 cos n theta depending on the power. If I rather subtract the inverse of a complex number from itself, then I'll get 2 minus sine n theta. How do we prove this? Remember that the inverse is the same as what we call conjugate. So the conjugate of a complex number, okay, is simply the conjugate in this sense. So let's see something. I'm going to have my z, okay, so let's z to be equal to cosine theta plus I sine theta. Okay, once I make this, it means that my z to the power n here is simply going to be what? Cos. So now please, since I have shown you the de Moivre's theorem, let me apply the de Moivre's theorem straight away. Okay, so this gives me cosine n theta plus I sine n theta, assuming that this is a unit complex number, meaning the modulus is 1. Once I do this plus the inverse, so the inverse here is the same as what? Replacing wherever I see n with negative n, because this is the same as z to the power negative n, right? So I'm simply going to have cosine n, but the n here instead of negative, cosine is an even function. So take note, cosine is an even function. If I put negative n or n is still n, right? So n theta. But here sine is an odd function, so I'll get minus I sine n theta. Okay, once I do this, what am I getting? So I'm going to get cosine plus cosine, which is 2 cosine n theta. Sine and sine cancels, and that is it. So that is what you can see from our identity here. Okay, so from our identity here, you can clearly see that we have proven it here. We can do same for the other identity which we have here. So in this case, I'm going to subtract cosine n theta minus, right, minus I sine n theta. Is that not it? Is equal to, what am I getting? Oh, sorry. Let me do it well. So we are proving for this section. So with this section to prove, the first one is cos n theta plus I sine n theta. Is that not it? Minus the inverse. So the inverse, I open my bracket, cosine n theta minus I sine n theta. Okay. So once I have this achieved, I'll close my bracket. Then what do? I expand. Cosine n theta minus cosine n theta. That will go to 0, right? I have plus I sine n theta. Minus is plus I sine n theta, right? Once I do that, this gives me what? 0. It goes away. But let's see something here. So I said this gives us what? 2I sine what? N theta. Is that not it? I omitted the n here. So please, there is an n here. I simply write n sine n theta. So I'm going to have 2I sine n theta. So these are the two identities proving why we have this. Let's look at the special case scenarios. So for the special case scenarios, when n is equal to, so when n is equal to 1, you are going to have z plus 1 over z is equal to 2i sine, 2i cos theta. Then z minus 1 over z is equal to 2i sine theta. So these are the two special case scenarios, okay? Two special cases. Now let's use this to solve a question for you to understand the essence of what that we are doing. So let's take our first problem. So it says that express sine 3 theta and cos 3 theta in terms of powers of cos theta and sine theta. So there's a problem. We have to express sine 3 theta and cos 3 theta in terms of cos theta and sine theta. Let's see how we can solve this problem. So using the Moivre's theorem, we realize that sine 3 theta plus cos 3 theta, right? Here, this is simply, right? So here, I'm just trying to show you something here. So let me put my I imaginary, or let me go straight to the point. So if I have cosine 3 theta plus I sine 3 theta, this is obviously going to give me what? Cos theta plus I sine theta all to the power. So this is reverse de Moivre's theorem, right? So de Moivre's theorem says that if you have sine 3 theta, you can put your theta as a power, and this is what we get. So at this point, we expand this using the binomial expansion. Since it is to the power 3, the expansion is 1, 3, 3, 1, the coefficient of expansions. So we are going to apply that. So the first one gives us cosine cube theta, right, plus 3 multiplying, that's the coefficient, cosine squared theta sine theta, plus another 3 multiplying cosine theta, no squared, sine squared theta, then finally sine cube theta. This is where I have omitted the I. So let me introduce my I. So I have my I here, I sine. One I is here. Wherever I see sine, I introduce my I, and I introduce my I here. Okay. So now let's see what you have. So once I come here, I have cos cube theta plus 3 cos squared theta I sine theta. Now this one, I was squaring the sine I sine theta all squared, okay? So meaning that I becomes negative, right? So we get negative 3 cosine theta sine squared theta. Take note. Here you are cubing. Remember when you cube I, what do you get? I cube. This is the same as I squared times I, where I squared is negative 1, so it's negative I, okay? So I cube is negative I. So I simply come here, negative I sine cube. Now I have my left side cos 3 theta plus I sine 3 theta. So you realize that at this point, I can equate my raw part to my raw part, imaginary part to imaginary part. Okay, raw part will be any part where we don't have I, where the imaginary part is where we have I. We equalize. So let me isolate all the raw parts here. So I'll have cosine cube theta, then minus 3 cos theta sine squared theta. Is that not it? Then I'll have plus 3 cos squared theta I sine theta, then minus I sine cube theta. Okay, so at this point I'll say that separating or comparing cos 3 theta on the left, which is the raw part, should be equal to, what do I have here, cos cube theta minus 3 cos squared theta sine squared theta, right? Then I'll have sine 3 theta to be equal to this part, so 3 cos squared theta. So I think this one I shouldn't have brought a squared. I made a mistake here. So yes, so 3 cos squared theta, 3 cos squared theta plus I sine theta, then minus I sine cube theta. So here we have been able to separate it. The question said we should express sine 3 theta and cos theta in terms of powers of cos theta and sine theta, right? So let's see something here. So here, remember that we are equalizing our i's, okay? So for the first part, let me use red. So for this part, I have cos cube theta minus 3 cos theta sine squared theta. So you know generally that sine squared theta is the same as 1 minus cos squared theta. Is that not it? So I can express everything in cos. So cos cube theta minus 3 cos theta, open bracket, 1 minus cos squared theta. Then this gives me cos cube theta, right, minus 3 cos theta, then plus 3, so let me come down, so plus 3 cos cube theta. Is that not it? Now let's do that for this. For this one, the first thing is to remove your I. So you factorize I on the left side. So factorizing I on the left side, what am I going to get? So for this, I think you let me change the second one. Let's finish the first one, then we do the groupings as well so that it doesn't conflict. So at this point, what I have here, I will say that I'm going to I have my cos cube theta here plus 3 cos cube theta, right? I have minus, so cos cube theta plus 3 cos theta minus 3 cos theta. So what's the answer? The answer is 4 cos cube theta minus 3 cos theta, and that is expressed. That is it. Let's check the second part. The second part is this one. This is what I'm trying to say, the imaginary part. So I sine 3 theta should give us all the imaginary parts which I grouped here. So I'll have 3 cos squared theta I sine theta minus I sine u theta. Okay, so at this point, you can see that I can factorize my I out and I'll get 3 cos squared theta sine theta minus sine cube theta, so that the I will cancel the I have here. So my sine cube theta now becomes 3 cosine squared theta sine theta minus sine cube theta. So at this point, this cos squared theta is the same as 1 minus sine squared theta, right? So 3 open bracket 1 minus sine squared theta multiplying sine theta minus sine cube theta. Once I have this written, I'll multiply. So I have 3 times 1 is 3 minus sine squared theta, which becomes 3 sine squared theta. Okay. So I think the sine theta here should multiply with the 3. I don't want to come back and multiply with the sine again. Long. So now let me say that I'm multiplying 3 times sine theta times this. So 3 sine theta times 1 is 3 sine theta. 3 sine theta times it gives us negative 3 sine cube theta, then minus sine cube theta. So I'll simply get 3 sine theta minus 4 sine cube theta, and this has also been expressed nicely. So this is our answer. We realize that I've expressed sine cube 3 theta into what? 3 sine theta 4 sine cube theta, and I've expressed cos 3 theta into what? 4 cos, oh sorry, 4 cube theta minus 3 cos theta, and that is all. So this is how you can use the Moivre's theorem to express trig identities. So that is it, right? Now let's see another beautiful example. Example 2, right? With this example, it says find an expression for cos cube theta in terms of cos 3 theta and cos theta. So the first question was to express cos 3 theta in terms of the cosine cubic of the cosines, but here we are going the inverse or the other way around, where we are trying to express cos cube theta rather in terms of cos 3 theta and not cos theta. Okay, so how do we do this? How do we express this way? We have to express cos cube theta in terms of this. Well, now this is where we use the nice principle that we have here. Remember there was this formula we wrote that z plus 1 over z is equal to 2 cos theta, right? 2 cos theta. Or the general formula said z to the power n plus 1 over z to the power n is equal to 2 cos n theta. Here's what I'm talking about. So see how this question will be solved. Since we are finding an expression for only cos, that is why we are targeting the cosine part of our identity. So there's no need for us to go and square like the one we did right now. You need to find both sine parts and compare. I mean, that is long. So here we move straight to the identity using this or this, right? So now let's check. If I have cos cube theta, okay, what does that mean? So check. So here, what do? I simply make to this cos theta the subject, then cube it. So to make cos theta the subject, let me take this off. Make cos theta the subject, what do? I'll say that 1 over 2 multiplying z plus 1 over z like this is equal to cosine theta, right? But we are looking for cos cube theta, so I'll simply cube everything. Then everything here will be cubed. Is that not it? So therefore, our expression now becomes cos cube theta is simply equal to 1 out of 8 multiplying the expression z plus 1 over z all cubed. That's the first step. Now what do we do from here? We use the binomial expansion to expand this with coefficient 1, 3, 3, 1. So I have cos cube theta is equal to 1 out of 8. We don't touch it. Inside I'll have z cube, that's the first coefficient 1, times 3 times their products. Okay, so with their products they are going to get so the first one is z cube, right? So this one becomes z squared times 1 over z. That gives me what? Z. Cancel to give me z. Then I move to plus 3 again, but this time I'll have 1 over z squared multiplying z, so I'll have 3 over z, then finally plus 1. over z cube, like this, nicely. Here's the second step. Now the third step. So cos cube theta 1 over 8 still. Here I'll group my like powers. So z cube plus 1 over z cube. They are like powers. Plus here too. Remember, I'll have 3 outside. Z plus 1 over z. So I now have two different powers. Is that not it? 1 and 3 separated. Then at this point, I'll simply have to multiply through by 1 over 8. So my cos cube theta will be equal to 1 over 8 multiplying z cube plus 1 over z cube plus 3 over 8 multiplying z plus 1 over z. Nicely. So you are supposed to express this in terms of what? The question says that you are expressing that in terms of cos 3 theta. Terms of cos 3 theta and cos theta. Obviously, you can see that this here, you can express this in terms of what? Cos 3 theta. Is that not it? So let's come here. What does this mean? Z to the power n plus 1 over z to the power n is always equal to 2 cos n theta. So meaning this becomes what? 2 cos 3 theta. Then this multiplies the 1 over 8 we have outside nicely. Plus 3 over 8. This becomes what? 2 cos what? Theta. So that our final answer becomes, using yellow to write, becomes 1 over 4 cosine 3 theta plus 3 over 4 cos theta, and that is our answer. So this is simply how we can use the Moivre's theorem to simplify trig identity. Okay, now let's look at one more applications of the Moivre's theorem for us to complete the Moivre's theorem. So let me go back and teach you one more application. So I'll simply have, let me, okay, let me use where I've cleaned up to. So here we are going to talk about nth root of unity. Nth root of unity. Nth roots of unity. So one application of the Moivre's theorem is for finding the nth root of unity. Okay, so it's used for solving equations in the general form z to the power n is equal to 1. Take note. On the Argand diagram, you can clearly see that, oh sorry, so you can visit our Argand diagram videos. So you can clearly see that this is our raw part and this is where you can look at 1. Is that not it? And argument is supposed to be the angle your complex number makes with the positive real axis. Here 1 falls on itself, so the argument theta is equal to 0. Therefore z to the power n is equal to 1. Converting 1 into polar form, I'll have z to the power n is equal to e to the power, because magnitude is 1, so I'll have 2 pi I k, as simple as that. Where the 2 pi k is simply for the extended argument, okay, for number of rotation, but the actual theta is 0. So now for us to find the nth root of unity, it means that z is simply going to be equal to e to the power 2 pi I k all over n, as simple as that. So we find the values when n is equal to 0, n is equal to 1, so n is equal to n minus 1, like that, simply. Let me take a problem for you to understand or appreciate this nicely. So the problem says that find the solutions to the equation z cube is equal to 1. To find the solutions to this equation z cube is equal to 1, what do we do? First of all, c cube is equal to 1. I said the next thing is to convert 1 to what? A complex polar representation. So z cubed then becomes e to the power 2 pi I k. Then at this point, z will be equal to 2. Oh, so at this point, e to the power 2 pi I k all to the power 1 over 3, because we take the third root on both sides. So at this point, my z becomes, or z is equal to e to the power 2 pi I k over 3. Now comes the roots of this we are talking about. So I'll find when k equals 0, k equals 1, and k is equal to 2, because it's z cubed, as I said, to n minus 1. So when k is equal to 0, our z1 becomes e to the power 2 pi I times 0 over 3, which is the same as what? 1. So everything here becomes 0, e to the power 0 is 1. My z2 is simply equal to e to the power 2 pi I, my k is 1, right? All over 3. So this gives e to the power 2 pi I over 3. My z3 is simply equal to e to the power 2 pi I times 2. That's equal to e to the power 4 pi I over 3. And that is all. So this is how you find the nth root of unity, okay? And this is all for this lesson. Thank you. See you in the next lesson. Don't forget to subscribe, like, and share.